Hi, I'm Jason. Welcome to Module 5, Fluid Statics and Dynamics. So we had a little bit of a slowdown last week. I applied some feedback and some lessons learned I had from last year. Though I wasn't teaching the whole course last year, I only had a couple snippets of it. I'd gotten a lot of feedback that there was a lot of overlap and between this and advanced thermodynamics. It was almost a repeat. So I've started looking at what material do we really need to cover here, and I've gone back through the old syllabuses, and so turns out thermocycles is probably a little too much. Now you basically need to know what a Rankine cycle is and what those points are. You need to know what the pump process looks like. You need to know what the boiler process looks like, both from the sensible heat perspective and the latent heat perspective. You need to know what a turbine process looks like, and then you need to know, of course, what the heat rejection process, the condenser, the cooling, removing of the heat from the condensate looks like. We're not going to get into any work calculations for whole processes. If for those of you that are going on to be operators or go through the operator course, we will visit this in advanced thermodynamics, and then that will be, hey, this is new stuff, rather than why are we doing this again? So, and I've a lot of good feedback that some of you are taking on multiple courses. The chemistry one sounds like it's a little tough right now. I'm trying to balance. I don't want to just give up and make it easy on you just to make it easy, but I want to make sure you're getting the right stuff without overdoing it. I don't know if that makes sense or not. But this week we're going to get into fluid statics and dynamics. So we've got 3 modules left: fluid statics and dynamics, and then we do heat transfer, and then we end this course out with pump theory, pump laws, pump theory. So you'll see that I put a PowerPoint in for this week, and I included the PowerPoint file as well as the PDF, the notes view of the PDF. So whichever format works best for you. So we're going to go through it in a couple of different parts. So when we're talking about a fluid can be either a liquid or a gas. A fluid is both. All gases are fluids, but not all fluids are gases. You may have heard all scotch is whiskey, not all whiskey is scotch. Just the same way with liquids. All liquids are fluids, not all fluids are liquids. Sometimes a fluid is a liquid, sometimes a fluid is a gas. So we generically talk about fluids so that we don't have to differentiate between the liquid and the gas, especially with what we're talking about, right? We have this boiling water reactor with this 2-phase mixture going on in the fuel channels where the bubbles start off, move to the center of the channel. Some of them are collapsing, but as this coolant moves up through, some of it remains steam, and this steam has a quality to it. So it's part water, part steam, right? So it's either way, it's a fluid. So we can just say fluid. This fluid is moving up through the coolant channels, and we don't have to be that specific about where it is in its phase change. So that's what a fluid is. By definition, that means what fluids are doing at rest. There's 2 main ideas to understand, and one of them is Archimedes' buoyancy principle, and then Pascal's law. The text in the PowerPoint walk you through those pretty straightforward. The goal of understanding those is to be able to solve a hydraulic problem, right? For those of you that say mountain bike and you've got the hydraulic brakes now that a lot of people use. None of my bikes have. None of my bikes. Like, I've got a lot of bikes. Neither of my bikes have hydraulic brakes, but I'm old-fashioned, so. A lot of new brakes out there have hydraulic brakes, and so this is the principles behind how those work and why those work. The brakes in your car, hydraulic, the hydraulic principles, right? You have a master cylinder, slave cylinder. Why does X number of foot-pounds of force of pressure on the pedal, which really isn't a lot, when you think about how hard you're pushing with your foot on your brakes, translate to thousands and thousands of foot-pounds of force on your calipers, right? And it's a series of pistons. It's a series of hydraulic problems based on Archimedes' principle and of buoyancy and Pascal's law, mostly Pascal's law, along with solving a force problem, the difference in force across a hydraulic piston. So that's going to be the fluid statics part of it. Fluid dynamics is what's going on with a fluid in motion. So from fluid dynamics, the big concepts to get out of this are volumetric flow rate and mass flow rate. On the surface, they're going to seem like the same thing, but they're not, okay? And it's important to understand which one to talk about, which one to use, and why. If I have some fluid going through a pipe, right, that fluid has a velocity. If I just measure the velocity of the fluid, then I know that velocity of the fluid. If I want a flow rate, I can look at a volume of that fluid. So I take a 1 cubic foot slug of that fluid and I measure it flowing past a point over a period of time. Now I know what volume past a point per unit time. Mass flow rate's the same idea, but it takes into account density. So instead of just the volume, right, which can be any amount of mass, if the hotter the steam is, the more expanded it is, the less mass is in that same volume, right? But the more, if it's cooled down, if it's more liquid, then it's going to be a lot more mass in that same volume. So sometimes it's not useful to measure the volumetric flow rate. Sometimes it's better to measure the mass flow rate. If you need to know how many pounds mass are flowing past a point per unit time. So differentiating between volumetric flow rate and mass flow rate is the important part of the fluid dynamics. So when I mentioned that we tend to use volumetric flow rates for one thing and mass flow rates for another, where the mass flow rate, where density matters, would make more sense for steam, right? So gases, when we're measuring gas flow, we use mass flow rate. And that's why a lot of these problems, these example problems, I'll say, hey, you have 12 pounds mass of steam flowing past a point at some speed, some velocity, 150 feet per second. And then you figure out, the mass flow rate. Our nuclear power plant, our steam flow rates are measured in mass flow rate. And it's 1.08 million pounds mass per hour. So it's a lot of steam flow. Volumetric flow rate is most often used for liquids, right? Liquids are non-compressible. The density change isn't going to be as significant. If it's cooler or hotter, it's not as big of a change in the mass that's in that volume. And so a volumetric flow rate, it's simpler. It doesn't take into account the density. And yeah, when we're talking about liquid flows, we're often talking about volumetric flow rates. An example of a volumetric flow rate would be cubic feet per minute, right? So that's most often used for liquids. Once again, mass flow rate for gases, volumetric flow rate for liquids. When we're talking about fluid flows, one of the things that matter is whether it's laminar flow or turbulent flow. And all this is going to be, you're going to see a bunch of stuff both in your text and in the PowerPoint. This talks about Reynolds numbers and Stokes units, and I don't even know those, right? I read them, I learned about them, moved on. The idea is, thicker things flow differently than thinner. Thicker fluids flow differently than thinner fluids. I think we already know that, right? So it has A thick fluid will have a certain flow profile as it's flowing through a pipe. A thinner fluid will have a different flow profile. And it kind of depends on how thick the fluid. If the fluid is thicker, it's going to tend to stick, the layers are going to tend to stick to each other more, and then to the side of the pipe, the wall of the pipe. And so it's going to have a more rounded flow profile, whereas a thinner fluid, those layers aren't sticking to each other as much. And that center line of that pipe is where the fluid is flowing the fastest. So it's going to have a more nose cone, rocket nose cone looking flow profile. Generally, we talk about flow through a pipe in average fluid velocity. So we would interpolate based on that flow profile what the average fluid velocity is using the center line speed and then some estimation based on the flow profile. The other thing that matters is laminar or turbulent flow. As far as laminar or turbulent flow is how heat is transferred, and you're going to see that in the next module, where heat is better transferred with turbulent flow, right? You get a better mixing of fluids, whereas with laminar flow, heat is transferred more gradually from the wall of the pipe to the center line of the fluid, or the center line of the fluid to the wall of the pipe, either way. And so these things matter when you're designing a system. Hey, I've got this liquid system, and I need it to have a lot of heat transfer. Okay, I'm going to design it to have turbulent flow. Well, how do I create turbulent flow? Well, I have to know those boundary layers. I have to understand the Reynolds number, the idea of viscosity, and how to create that turbulence, whether a wider pipe or a thinner pipe creates more turbulence, whether a higher fluid flow or a slower fluid flow creates more turbulence. So these are all the ideas behind designing a hydraulic system. Then we get to the one that seems to scare people, but it shouldn't. We introduced you to the general energy equation pretty early on. The reason we introduced you to the general energy equation early on was to get you used to the ideas that it's just adding up work in a system, right? Energies. Bernoulli's equation is just it's a stripped down version of the general energy equation. So don't let it frighten you too bad. It's just looking at a couple of the terms in there, and it kind of simplifies the general energy equation for a specific idea, for fluid flow between 2 points. Whether they're at different heights or the same height, right? If they're different heights, you use the potential energy piece of it as well. But it's talking about the flow energy and the speed of the fluid, right? What we're going to do this week is work through some problems. I want you to read the text, pages, I believe it's 92 through 105. Yeah, so it's 13 pages. Don't worry too much about the Reynolds numbers, Stokes, that detailed thing on the viscosity, right? All that, the shearing force is just trying to get the idea that, yeah, if I have a pipe, right? If I have a pipe and I have fluid flowing through that pipe, the fluid flowing through the center is going to be traveling faster than the fluid that's got the friction on the edge. And so it's talking about what that flow profile looks like. That's it. But look at the idea behind the Archimedes principle and Pascal's law. Look at how to solve a hydraulic problem, right? The difference in surface area on a piston, which is the application of those. Look at the fluid dynamics, the volumetric flow rate and the mass flow rate. Those are going to be important. I do need you to solve those. And then for Bernoulli's equation, yeah, we need to be able to apply that for fluids. So for your evaluation for this week, after you read the material, do the PowerPoints, watch any other videos I put up, is we're going to do a quiz, but I like how we did that quiz, the multiple attempts. Even if I get what you could do is open the quiz, do the quiz, see the right answers, be like, okay, I'm going to go now I'm going to say that. I hope you don't do that, but that's going to be a personal choice. I will make it available to do multiple attempts, probably two, so that you can get a better score, but more so that I want you to go in and answer correctly where possible. You learn more that way. You're more likely to remember the concept, the idea, the theory, if you've answered a question correctly. Ultimately, the end goal for this module this week is be able to apply the hydraulic principles, the flow rate, whether it's mass flow rate or volumetric flow rate, the idea of how fluid flows, and solve and all into Bernoulli's equation and solve a problem like the example problem in your PowerPoint where water's pumped from one reservoir to another reservoir at a different height, right? How hard does that pump have to work to move that fluid? If you're designing a solar water heating system for your house, you can use these ideas to figure out what size pump you need to buy in order to move the fluid from whatever the lowest point in the system is to up through the pipes on your roof and through the system. So it's, figuring out work of a system using Bernoulli's equation, pump head. As always, if you have any questions, use the questions for the professor, and I hope you have a great week. Thanks.